will start. The first question that we are taking is this one. It is given that the magnetic flux linked with a coil is given as a function of time. Okay, so it is dependent upon time. Phi is given as a function of time. It is given as phi t is equal to 3t square plus 4t plus 1, and we are supposed to calculate the instantaneous EMF at t equal to 2 seconds. That means the EMF at that particular point of time, as well as the average EMF between t equal to 0 to t equal to 2 seconds. That means there are two things that we are supposed to find out. One is instantaneous EMF, whose formula is E is equal to d phi over dt. Okay, and if we include the Lenz's law, it is going to be minus d phi over dt, as d phi over dt gives the magnitude of the induced EMF, and minus sign shows the direction of that induced EMF. Okay, so what is minus sign supposed of? Okay, see, minus sign shows that whatever be the change in magnetic flux, whatever be the direction of change in magnetic flux, or whatever be the cause of change in magnetic flux, the induced EMF is going to be in such a direction that it will oppose the change in magnetic flux. Okay, now, so E is equal to d phi over dt. This we use always for the instantaneous thing. Whenever we are using d phi over dt, this is for instantaneous. For example, for calculation of instantaneous velocity, we used to do V equal to ds over dt. For instantaneous acceleration A, we used to do dv over dt. For instantaneous angular acceleration, we can do d omega over dt. Similarly, for instantaneous induced EMF, we are going to do E is equal to d phi over dt. Okay. Now, so E is equal to ddt of phi. Whatever we are having as phi is right here, 3t square plus 4t plus 1. 3t square plus 4t plus 1. We are going to differentiate it. Okay, so that is going to be 3 times ddt of t square plus 4 times ddt of t plus ddt of 1. Okay, now we are supposed to use some kind of formula for differentiation here. Okay, so the most basic formula for differentiation that we are going to use is d dx of x to the power n is equal to n times x to the power n minus 1. Okay, there is a big proof of this formula using binomial theorem. Okay, and first principle. Okay, we don't need to prove the formula. We know the value n times x to the power n minus 1. Okay, so from here the value of induced EMF, the instantaneous induced EMF, is equal to 3 times ddt of t square is going to be 2t plus 4 times ddt of t will be just 1, or you can consider t to the power 1. That means after differentiation it will be 1 times t to the power 1 minus 1, 0. So t to the power 0 will be 1. So 4 times just 1 plus differentiation of anything is going to be 0 if it is a constant. Okay, differentiation of anything constant is going to be 0. See, why is the differentiation of anything constant is equal to 0? Because the differentiation value or the dy over dx value actually gives you the tan of angle that the graph at that point of time makes with the positive x-axis. Okay, now when something is constant, that means it's not changing with respect to y. This is your y-axis, this is your x-axis. If something is constant, I'll draw a graph just to brief you. Okay, this is y versus x curve. Okay, if something is constant, that means its graph is going to be parallel to the x-axis, and if it is parallel to the x-axis, it means that it is not changing. It's not changing, or the angle that it is making with the x-axis is going to be 0, and the geometrical interpretation of slope or dy over dx is nothing but tan of the angle that the slope is making with the positive x-axis, which in our case is 0. So tan 0 is going to be equal to 0. Okay, so as you can say, differentiation of anything constant is going to be 0. Okay, now let's move forward. Okay, so EMF is going to be 60 plus 4. Okay, now EMF also you can see is a function of time. So in order to get the exact value of EMF at a given time, we need to put the value of time in that equation. Okay, so EMF at t equal to 2 will be equal to 6 times 2 plus 4, that will be 12 plus 4, that is 16, and EMF SI unit is volt, so it's going to be 16 volt. So this value that we have got for EMF is the instantaneous value of EMF. Now let us calculate the average value. So for average value we are having E average equal to delta phi upon delta t. Okay. See, the difference between instantaneous and average values are कि instantaneous values are for a given point of time or a given instant of time. Rather, the average value is for a given period of time or in between some interval. Okay. So delta phi over delta t means the difference of the magnetic flux between 2 points, between 2 values of time. Okay. So it's going to be E average is equal to, we are supposed to find out between time t equal to 0 to time t equal to 2 seconds. So I can say it's going to be phi 2 flux at time t equal to 2, instantaneous flux at time t equal to 2 minus instantaneous flux at time t equal to 0 upon the difference in time, that is going to be 2 minus 0 only, so 2. Okay. So E average will be equal to phi 2. Now I will put the value of time t equal to 2 in this equation. Okay. So it's going to be 2 to the 4, 4 3s are 12, 12 plus 2 4s are 8 plus 1. Okay. Minus, when I put 0, we just get 1. Okay. Upon 2. Okay. Let's check again. When putting t equal to 2, 2 to the 4 3s are 12 plus 4 to the 8 plus 1. Yeah, absolutely fine. So this 1 will get cancelled and we'll have 12 plus 8, 20 upon 2, that is going to be 10 value. Okay. Or the 10 volt. So EMF induced in between the two time, like t equal to 0 to t equal to 2, or in an interval of 2 seconds, t equal to 0 to t equal to 2 seconds, is going to be 10 volt. Okay. So I hope the difference between the instantaneous EMF and the average EMF is clear to you. Okay. So instantaneous EMF is going to be 16 volt, average EMF is going to be 10 volt. Now they may ask questions like at what point of time the instantaneous EMF can be equal to the average EMF. Okay. In that case, we'll have to find the answer in terms of time and then we'll equate it. For example, instantaneous EMF is equal to 60 plus 4 and the average EMF we can calculate in terms of time again. Okay. And then we can equate both the equations to have a particular value of time such that both instantaneous as well as average EMF are turning out to be same. Okay. I hope this this solution is clear to you. Let's move on to the next topic. So guys, the second category of important problems is the rail problems in electromagnetic induction. Okay. So I'll explain you the setup first and then we'll start solving the questions. Okay. So in the setup they have given that these are two conducting rails, okay, which are connected through a wire and a resistance, external resistance capital R. Okay. And these rails are placed in a uniform magnetic field directing inwards perpendicular to the plane of the board. And there is a conducting rod which is sliding on these frictionless rails. Okay, friction is not given. However, in some questions they may include friction as well in order to make the question further complex. Okay, so as of now the friction is not given. This rod is conducting. Okay, it could be of copper or like iron. Okay, and it is sliding on these two rails with a velocity v0. Okay, now they are asking these three questions: find the motional EMF and current in the rod. Find the force required to keep the rod moving with a constant velocity v0, and then the third one, find the input power and the output power. Okay. However, the length of this rod is given as L and the internal resistance of the rod is given as small r. So small r is the internal resistance. Okay. Let's start doing the question. Okay. Now we know that in motional EMF, okay, when the rod is sliding, definitely there will be a EMF induced in the coil. The reason for that induced EMF is that the area inside this coil, the area inside this imaginary coil is changing as the rod is moving in this direction with some velocity v0. Okay. Now as it is moving, since the area is changing, the number of lines of force going inside into that particular area is also increasing, or in turn the flux is increasing. And we know according to Faraday's law, if the flux keeps on increasing or decreasing, then as a result of that change in flux, some EMF is induced. Okay. Now the EMF induced is given as EMF, motional EMF, E is equal to V cross B dot L. Okay, V cross B dot L. Now in this case the motional EMF will be how much? Let's try to calculate. Velocity is in this direction, magnetic field is in inwards. So we'll stretch our right hand, okay, and we'll use the cross product rule or the V is in this direction, B is inwards. So V cross B, the direction of thumb is upwards. That means V cross B and L both are in the same direction, or the angle between V cross B vector and length vector is 0, and cos 0 we know is equal to 1, and hence the EMF value, the motional EMF value will be reduced to BLV, which means that this moving conducting rod will start behaving as a battery. Okay, will start behaving as a cell. Okay, that means we can redraw the circuit like this. Okay, this was your external resistance capital R. Okay, these are the conducting wires, or like I'm drawing conducting wires, and these rails as some conductor. Okay, this is having a length L with internal resistance small r, internal resistance small r. Okay, and then the battery is going to be upside down. That means V cross B is going to give you the direction of induced current. V is in this direction, B is inwards, so V cross B is in the upward direction. That means the positive terminal has to be upwards and the negative terminal has to be downwards. So this is small r, this is capital R, and this is going to be E. Okay, the EMF induced in the battery. Okay, as a result of this EMF, there will be some current, and that current obviously will be the induced current. Okay, so induced current I will be equal to the EMF induced upon the net resistance of the coil, or the net resistance of the circuit, that is going to be capital R plus small r, because both of them are in series. So I can write I is equal to capital R plus small r, that is the value of current. Okay, find the motional EMF and current in the rod that we have found out. So the first part of the question is motional EMF is BLV, and the current induced is E upon R plus R, or I can write I is equal to BLV upon R plus R. BLV upon R plus R, that is the value of induced current. Now the second thing that they are asking, find the force required to keep the rod moving with a constant velocity. See guys, let's try to understand the concept behind it. As it is moving in this direction, this is the current carrying conductor now. And whenever a current carrying conductor is placed inside a uniform magnetic field or even a non-uniform magnetic field, it starts experiencing some force, and that force is given by F is equal to I times L cross B. Okay, or we write it as ILB sin theta. Okay, F is equal to IL cross B, or F is equal to ILB sin theta. Now, as it is moving in this direction, let's try to find out the direction of force it is experiencing, or the direction of magnetic force that it is experiencing. Okay, so length vector is in this direction, magnetic field is inwards. Why am I telling length vector is in this direction? Because conventionally we correct the direction of length vector to be in the direction of current. So current is in this direction, length vector also we are considering in this direction. L cross B, guys, L cross B is going to be this direction. Now if I draw the free body diagram of that current carrying wire, or this current carrying rod, which was moving, it's V naught. Okay, we know that it is moving with a velocity V naught in this direction, and the magnetic force is inwards. Okay, that means the direction of force and the direction of velocity are opposite. Okay, hence deceleration can be expected. Okay, whenever the direction of acceleration and the direction of velocity are opposite, definitely the speed reduces, and contrary to this, when the direction of velocity and the direction of acceleration are same, the speed keeps on increasing. You can take the example of gravity. As it was moving upwards, acceleration was in the downward direction, but velocity in the upward direction, and hence you can see speed was decreasing. Maybe it started with 5 meters per second, kept on reducing, 4, 3, 2, and then finally at that topmost point, the speed was 0. Speed becomes 0 means this is the reason why it is not going further in the upward direction, it is coming back now, coming downwards now. Now when it started from top, the initial velocity was 0. Okay. Now from the top, the acceleration and the velocity both were in the same direction, and hence speed keeps on increasing. 0, 1, 2, 3, 4, 5, 6, whatever. And when it reaches the same height or the same level from where it was thrown, at that point it will be having the exact same speed, ignoring the air resistance and everything. Okay, macrophysics. Okay. So I can say the force is in this direction, velocity is in the opposite direction, and hence you can say it's going to reduce. The speed is going to reduce, or it's going to deaccelerate, you can say. Okay. That means in order to keep it moving with the same velocity v naught, that's what they're asking. That means acceleration should be 0. Okay. So acceleration of that rod should be 0 if velocity v naught has to remain constant. Okay. Now if velocity has to be constant, acceleration has to be 0, can I say the net force on it also should be 0? Net force on it also should be 0. And if the force is 0, that means you need to apply an external force on the opposite direction, which should be of equal magnitude as the magnitude of magnetic force. Okay, that's how we can make the net force to be 0. Okay, so F external force is going to be equal to ILB, the same value. One more thing, L and B are perpendicular to each other. L and B are perpendicular to each other, and therefore we can say sin theta is going to be 1, theta equal to 90. So force will be ILB on B. Force will be ILB. Okay. Or external force that you are going to apply is I is BLB upon R plus R into L into B. So external force that you are going to apply is equal to B square L square V, B square L square V upon R plus R. That is the external force that you need to apply in order to make the rod continue moving with the velocity v naught. Okay. Now the third part of the question we are going to solve. Let me rub the board. So in the third question we are supposed to find out the value of power input and power output. Okay. First we need to realize what exactly will be the power input. See, the EMF is generated as a result of the constant velocity of the rod. Okay. When the rod is moving, it is deaccelerating also, and in order to keep it moving with a constant velocity, we are providing a force in this direction. Why? Because magnetic force was in this direction. So as a result of the external force that you are providing in this direction, there is some power. Okay. So power dissipated, or the power input, will be equal to work done per unit time, and this work has to be done by the external force that you will applying in this direction opposite to the magnetic force which was in this direction, such that both the forces cancel out each other, and this keeps on moving with a constant velocity v naught, thereby producing a constant induced EMF PL v naught all the time. Okay. So power input is equal to dW over dt, or power input is equal to dW can be written as F external dot dx over dt. Okay. I could have written vector sign and then could have solved, but then we know that F external and dx both are in the same direction, so cos 0 will be 1, so definitely it will come out to be F external into dx only. Now power input can be further written as F external into dx over dt. Okay. Dx over dt is the rate at which it is moving. Okay. So the rate at which it is moving is already given as v naught. So in place of dx over dt we can write v naught, or power input is equal to F external times v naught. F external we have b square L square v naught, b square L square v naught upon R plus R into v naught. Okay. So power input from here can be written as power input is equal to b square L square v naught square upon R plus R. That is the value of power input. Now we are supposed to find out the value of power output as well. Okay. What is power output? Actually, in case of a resistor or in case of any circuit element, the power is obtained across the potential difference of the circuit elements. Okay. So power obtained will be in these two resistors, the internal resistance of the rod as well as the external resistors that are connected with the rails. Okay. So power output, we know that P is equal to voltage into current. Okay. Or we can write P naught is equal to power output. V is equal to IR, so I can write I square R. Okay. Or power output is going to be I square, and the net resistance of this circuit is small r plus capital R, as we have drawn the circuit in the previous board, that the two resistances are in series, so the net resistance has to be capital R plus small r. So I square capital R plus small r, and hence P naught is equal to I square value. We have got the value of I will be BL V naught at the time when the velocity is V naught. Okay, so I can say B square L square V naught square upon R plus R whole square into R plus R. Okay, so this one R plus R and R plus R will get cancelled, and we'll have power output is equal to B square L square V naught square upon R plus R. Okay, that is the value of power output. Clear? Okay. Interestingly, the value of power input and power output are coming out to be same. Okay, P square L square V naught square upon R plus R. Although we have calculated power input using the external force formula, the work done per unit time formula, because that external force is the one responsible for bringing about that change. Okay, and power output we are obtaining by using the power dissipated around the or about the resistor. Okay, so both the different formulas we have used, and still we are getting the same values. Okay, which is a very ideal case. I'll say ideal case, the power input is equal to power output. That means in some cases you might be asked to find out the efficiency of such a machine or efficiency of such a coil. So efficiency is equal to power output upon power input into 100. Okay, so in this case efficiency is going to be 100%. Pi upon PO, or sorry, PO upon Pi will be 1. Okay, so 100%. But then ideally eta means efficiency is coming out to be 100% in our case, but we cannot ensure that any of the rail can be frictionless. Okay, there will be some friction being a non-conservative force. Definitely there will be some loss of energy in the form of heat, as it will keep on moving in the forward direction. It is going to have some kind of friction, and as a result of friction there will be some heat produced, although very minimal amount, but then that is going to ensure that minimal loss in heat will ensure that the power output is definitely going to be somewhat less than power input. Okay, you cannot have a machine which is going to have an efficiency equal to 100% or efficiency equal to 1. Okay, so this was one of the classical problems that they ask in electromagnetic induction, very important as well, and they keep on asking such questions. I hope you have understood it. So yet another important question that is asked in CBSE term 1 is what is the motional EMF in a rotating rod such that it is placed in a uniform magnetic field. So first of all we will try to understand what is this setup. Okay, they are telling that there is a uniform rod. Okay, uniform rod such that it is having a length L and it is pivoted about this point and is made to rotate with some constant angular velocity omega in a uniform magnetic field placed inside such that the magnetic field is pointing inwards, perpendicular to the plane of the board or perpendicular to the plane of the rod. Okay, now they are telling what is going to be the induced EMF as the rod starts rotating. Okay, so first of all let's try to understand why will the EMF be induced. The EMF is induced because this rod is moving. Okay, and for a moving rod or for a translating rod, the EMF induced is equal to BLV or L dot V cross B. That is what we have studied in the previous questions. Okay, so E is equal to BLV. What happens if it starts rotating? Okay, so this question becomes very important as a result of inclusion of both rotational mechanics as well as electromagnetic induction. Okay, how is the rotational mechanics involved? Let's try to understand. Now see, as it is rotating, all the particles on this rod is also rotating along with it. Okay, now the angular velocity of all the particles is going to be constant. However, the linear velocity is going to vary. Let's try to understand why is angular velocity constant and why is linear velocity varying. See, angular velocity is equal to change in angle upon change in time, or angular displacement upon time. Okay, now let's say it has reached somewhere here. Okay, after some time, let's say this is t equal to 0, this is t equal to some time t. Okay, now every particle has covered an equal angular displacement which is equal to theta. Let's say, assume. Okay, so whatever be the angular velocity of this particle is going to be the angular velocity of this particle. Okay, but then if we consider the linear velocity, it's going to be change in displacement upon change in time. all these particles, let's say this is A, B, C, D, okay. So these particles, as they keep on moving away from the pivoted point or the fixed point, definitely the displacement covered by each of them is going to be increasing. Displacement of this particle is more than the displacement of this particle, is more than the displacement of this particle, and as we keep on reaching towards the pivoted point is not at all displacing. Okay. So as we keep on moving away, the displacement keeps on increasing, and that is how we say V is equal to R omega. V is equal to R omega. That means V is equal to R omega, or V is directly proportional to R. Omega is constant for all the particles. As we keep on moving away from the point, that means as we keep on increasing the value of R, this V will also keep on increasing. Okay. So now let's try to analyze what will happen. Okay. Now, since the linear velocity of all the particles are different, we cannot apply this principle E equal to BLV, or we cannot apply this formula. Okay. Now that means different points on this particular rod is having different linear velocities. Okay, and that is going to change with the distance from this pivoted point. That means we need to do some kind of integration. Okay. Let us consider a particular element dx somewhere here, okay, at a distance x from the pivoted point, okay, such that it is moving with a velocity v. Okay. Now the small EMF induced in this dx element, the small EMF induced in this dx element is going to be how much? BLV. Okay, we'll write all the terms. What is B, what is L, and what is V? Okay, so for B, we write B. BE is equal to B into B. B is the magnetic field. Okay, constant one only. For L is the distance from the pivoted point. Okay, so for L, we can write just x or dx. Why? Because this is the length of the element is dx. So B into dx. And what is V? V is going to be R omega, and R is the distance of moment R, or R is the distance from the pivoted point. So in place of R, we can write x. So in place of V, we will be writing x times omega. Okay. So we have got dE, the small EMF induced, is equal to B times omega times x dx. B times omega times x dx. Okay. Now, if we have to calculate the net EMF which is induced in the entire rod, definitely some of the dx element can be considered here, some of the dx elements can be considered here, some of the dx elements can be considered here, and finally some of the dx elements can be considered here as well. That means the dx elements can be from L equal to 0 or x equal to 0 to x is equal to L. By doing that, by considering x from 0 to x is equal to L, we are including all those elemental charges, or like elements which are a part of this rod. So I can say E is equal to integration of B omega x dx. Okay. Now we are having a differential term of dx. That means we need to integrate in terms of x only. X is equal to 0 to x is equal to L. Okay. Or EMF induced is equal to B omega integration of x dx 0 to L. And as far as formula for integration of x dx is concerned, we have a formula: integration of x to the power n dx is equal to x to the power n plus 1 upon n plus 1 plus c if it is an indefinite integral. Okay. So but then it is a definite one, so we need not to add the constant of integration. So we write E is equal to B omega x square by 2 from 0 to L, and hence the value of EMF finally is going to be E equal to B omega L square by 2. That is the formula for, or that is the end result conclusion for EMF of a rotating rod placed in a uniform magnetic field such that the length of the rod is L and it is rotating with a constant angular velocity omega. I hope you have understood it. Let's move on to the next one.